Woodland Valley Stream, tributary to the Esopus, is an example of a freestone trout stream. Now, we'll talk about freestone, what that means a little bit later on. I know it doesn't look much like a trout stream now. The water is very low and very clear, but it's very cold, as my feet would attest to. My feet are freezing. There are trout in here. We've seen them as we've walked along the banks, and it's a good example to use when we're discussing the changes that occur in a stream from its headwaters, and we're not far from the headwaters of Woodland Valley, to the mouth of the stream, and ultimately we're talking about the mouth of the Esopus as it flows into the Hudson River. Basically, what we want to key on today is to look at these streams in regard to their evolution or change over the course of the stream. In a sense, it's not too different from the evolution we talked about with lakes, or even from terrestrial succession when we discuss going from the pioneer stage to the climax stage. These streams go through a similar type of change from their headwaters to their mouth. As I mentioned, this is considered a freestone stream. What we mean by freestone is it's a type of stream that doesn't drain through any kind of major sedimentary formations. Now, that doesn't mean there isn't some sedimentary rock within the overall drainage of Woodland Valley Stream. What it does mean is there's not a great deal of limestone, for example, that this water goes through. This has a major effect on its nutrient concentration. Basically, a stream such as Woodland Valley does not get a lot of nutrients, and you know we've talked about these many times, phosphate, nitrate, etc., from the substrate that it flows through. So that the nutrient input into this stream is primarily allochthonous. That is, if you recall, nutrients coming in from the land, forest, fields that surround the stream. Because of this, this will always be a slightly more sterile, or in some cases a great deal more sterile, than, let's say, a limestone bedrock stream. It is also a stream that starts from runoff. And that's, of course, why it's dropped so drastically from early summer, and it's been about 2 feet, to the present condition, very low water. Because the runoff is very low, because of the lack of rainfall, as I mentioned, it's been a fairly dry summer, this stream reflects this change, and it goes through a major change in water levels throughout the course of the year. Again, that is not true of streams that have major spring inputs, which is characteristic of limestone streams. With a great deal of springs, major springs, and groundwell input into the stream, aquifers, water levels don't change that drastically during the course of the year. Now, streams such as this would be characterized as being a good trout stream because it has a nice mixture of riffles and pools. Now, we're talking about streams in their upper reaches, that is, more towards the headwaters. There's a relatively steep gradient. All streams closer to the headwaters have a fairly steep gradient. By gradient, we mean the amount of vertical drop for the amount of horizontal distance covered. In other words, there's a great deal of drop as far as altitude is concerned for a relatively small amount of distance. This major gradient creates the ideal situation of primarily fast riffles and pools, which is perfect trout water. In fact, if you were doing a survey on this stream, one of the first things you'd want to do is to determine a pool to riffle ratio. Now, although that's sometimes listed as PR ratio, don't confuse that with photosynthesis to respiration that we've talked previously about as being a PR ratio. Better you just refer to this as pool to riffle ratio. Ideal is about half and half. The riffles are very important because the riffles mean there's a tremendous amount of interaction with the atmosphere, meaning that there is good respiratory gas exchange.